Dear student, good day. This video is intending to explaining the concepts of BJT amplifiers as learnt in class. So when it comes to BJT amplifiers, and this is now referring back to the notes that you were provided with, we start by looking at a quick revision of NPN as well as PNP transistors. This is because these are the two types of transistors that we use for designing a BJT amplifier. Let's start with an NPN transistor. NPN transistor, of which the electronic symbol is as follows. Sometimes you'll find it provided in that direction, but that's still the same device. Since it's a BJT transistor, bipolar junction transistor, it has got three terminals: a base terminal, a collector terminal, and emitter terminal. Same here: base, emitter, and collector. On the other side, the PNP transistor has got the following symbol. It also has an emitter, a collector, and a base. This is all things you've learned in Electronics 1, but that are very important to go back to. It's very important to go back to these basics. So the BJT transistor NPN, as you know, a BJT transistor in general, before speaking about NPN and PNP, is normally made up of two NP junctions, two PN junctions, let's call them like that. And this throws us back to the concept of diodes, which are made up of PN junctions. And we know what a PN junction, we know it is a depletion region, a barrier voltage, etc. So a BJT is made up of two PN junctions. The first one is the EBJ junction, or emitter base junction. Emitter base junction. We also have the CBJ, or collector base junction. Those are the two junctions that we have in a BJT transistor. So now the two PN junctions put together, depending on how they are put together, form what we call an NPN or a PNP transistor. So now, if you put a N type, a NP junction, meaning NP simply means you're putting a N-type semiconductor next to a P-type semiconductor to create a depletion region, they're called NP junction, next to a PN junction. So on one side you've got the NP junction, on the other side you've got the PN junction. Then you form what you call a NPN BJT, or bipolar junction transistor. On the other hand, if you put a P P-type junction next to a N-type junction, a PN junction. So a P-type semiconductor next to a N-type semiconductor form a PN junction. So you take a PN junction, you put it next to a NP junction on the other side. So P again. You form what you call a PNP BJT, or bipolar junction transistor. So I will not go back into the whole concept of PN and NP junctions, because the assumption is that you've covered this and you quite understand this in Electronics 1. However, there are also slides that are provided to you in terms of this, and these slides are titled diodes, just as a revision. But that was very important to establish and to make sure that you understand. Okay, now next to this basic construction concept of NPN and PNP transistors, is what we got into what we call DC analysis of um, of BJT transistor circuits, and this once more has been covered in Electronics 1. And in the DC analysis part of BJT transistor circuit, we start by defining a concept that we call biasing. Biasing a transistor, DC biasing to be specific, biasing a transistor consists of supplying it with DC power voltage in order to operate it at a certain VCE and at a certain IC. So there are two key elements that define the point at which a transistor is said to be biased. So to operate a transistor at a certain collector current IC and a certain VCE voltage consists of biasing it. So now there are many methods of biasing NPN or PNP transistor that you've learned in Electronics 1. We will not go back onto that, and I highly encourage you to revise that. But we're just gonna go into some basics when it comes to the different current flows in and voltages in a transistor. We shall recall that there is at the base in an NPN transistor, through the base flows a base current. At the collector, through the collector flows a collector current, and at the emitter of an NPN transistor flows out an emitter current. So we've got IC and IB flowing into the transistor and I flowing out of the transistor. By simple intuition, one can come up by applying Kirchhoff's current law, considering a transistor more or less like a node. You would come up with the sum of current going into the transistor, which is IB and IC being equal to IE. Just as revision. You also recall what we call beta of a transistor, which is a very important characteristic of a transistor, sometimes referred to as HFE. And HFE is nothing but what we call the DC current gain of a transistor. And that is defined as the ratio between the collector current and the base current, right? Collector current considered to be the output current and the base current considered to be the input current. So that is what we call beta. At the same time, you've defined also in Electronics 1 a parameter called alpha, which related the collector current to the emitter current. And you, thanks to these two definitions, you were able to establish the relationship between alpha and beta as alpha being beta over beta plus 1, simply because alpha is actually IC, which is nothing but beta IB, based on that first definition of beta. At the same time, IE is IB plus IC. So if you carry on, you'll get beta IB to be alpha to be equal to beta IB divided by IB plus IC, which is still beta IB once more. So if you carry on and you put IB as a common factor, you end up with beta over IB, which cancel. If you factorize there, you get beta plus 1, and that's how we'll end up with alpha being beta over beta plus 1. The same principles are applicable to a PNP transistor, with the only difference that the current directions change. So the emitter current is flowing that way. The collector current is flowing that way, and the base current is flowing out. If you apply Kirchhoff's current law once more, IE, which is the only current going into the transistor, is still equal to the sum of the two currents going out of the transistor, which are IB and IC. And the same definition of alpha applies, and the same definition of beta applies. So that in terms of current. When it comes to the different voltages, you recall that the transistor is made up of two junctions, and the EBJ junction as well as the the CBJ junction. On the EBJ junction, of course, we've got the voltage that for a NPN transistor is called VBE, and for a PNP similarly is called VEB. And we also have this on the CBJ junction what we call VCB, which is VBC for a PNP, VBC for a PNP. And at the same time, we also have a very important characteristic voltage of a transistor, which is VCE, that we're gonna also soon analyze. We're gonna carry on just now.